Last time we talked about molecular geometry, and again, we talked about many, many different molecular geometries, much more than what you saw in honors. In honors, you probably only learned about linear, trigonal planar, tetrahedral, trigonal pyramidal, and bent. At the AP level, we talked more about like 15 shapes. What were some of the shapes we learned about last time that you hadn't seen previously?
Seesaw.
Seesaw.
T-shaped.
T-shaped. What else? Octahedral. Square pyramidal. Trigonal bipyramidal. And square planar. Also be careful with the polarity piece. Last year you would have seen if there were lone pairs on a central atom, you were automatically going to have a polar molecule due to the asymmetric nature of the molecule. This year you can have lone pairs on central atoms and still have a nonpolar covalent molecule. And we'll take a look at that in a little bit with our drawings. We're going to talk a little bit about atomic orbital overlap. We're not going to get into valence bond theory all that much, but there are a couple of key points that I want you to be aware of. I'm going to draw over here. So what you're going to see, for example, is that we know that electrons are in orbitals. Orbitals are the most likely location of electron. There's a 90% probability that the electron is there. When you're talking about compounds, you have bonding electrons that are more restricted in regard to their movement. And we talked about this with compression of bond angles, why, for example, ammonia would have bond angles of 107 as opposed to 109.5 that tetrahedral electron group geometry shows, because the lone pairs of electrons can repel more than the bonding pairs, resulting in compression of a bond angle. Well, what you're going to see is that a covalent bond is formed when you have a shared pair of electrons with opposite spins in a certain region of overlap. The atomic orbitals overlap between two atoms. There's a very high electron charge density there. What you have is a molecular orbital where the electrons in the bond are more likely to be found. The more they overlap, the stronger the bond for the most part. What you're going to find here is that there is a specific way that you can learn about molecular geometry, first in regard to VSEPR that we talked about last time, and now you're going to see this valence bond theory. And we're going to take a look at this in the following way based on hybridization. Hybridization means a blending together. Think about some of the things you have now that might be hybrids. What might you have that's a hybrid? Or what have you heard of that's a hybrid? Steel is a hybrid of what? It's a combination of things. Bronze. I don't know if I would call it a hybrid, but it's a combination. You're actually going to be learning about that. They're called alloys, but you are correct.
Aren't there certain fruits that are hybrids?
Fruits that are hybrids? For sure. You get a blending together of two different fruits.
There's one cauliflower and broccoli, but I forgot what it's called.
Is there a combination of that? I've heard of pluots, like plums and apricots. They make pluots. See, you know because you eat healthy foods. What else is a hybrid? Anybody have a hybrid vehicle?
A liger.
A who?
A liger.
A liger? What's that?
Lion.
Does it exist?
Yeah. Yeah.
See? A blending together of two species.
But they don't keep very long. They live like a few months and then they die usually.
Do you know why?
Because their genes and stuff don't match up together.
Probably. So it's probably too many chromosome abnormalities, and so they're live births, but they don't live very long. And you see that even with humans too. Some genetic types of anomalies can survive where the child will be born, but they won't live very long due to the chromosome abnormalities. One key I hate to use the word anomaly, but one key chromosome abnormality where you do see survival and flourishment is with trisomy 21. So there, I don't really think it's a hybrid per se. You just have an extra copy, but you can have translocation of chromosomes. That usually doesn't last that long, but it would be interesting to look at the genetics of that to see exactly what's going on. That's your project over break. All right, in any event, hybridization is a blending together. We're going to blend atomic orbitals to produce new ones, and they are going to be, the new ones will be equivalent to one another in terms of energy and shape. For example, we can look at this in regard to S and P orbitals. Let's say, for example, that you have carbon. Carbon is 1s2, 2s2, 2p2. So if you look at the second shell, in terms of 2s, you've got this, and then remember you have 3 orbitals in the 2p subshell. As such, and what we're going to do is we can blend the s and p orbitals together to get either sp, sp2, or sp3. If we take one of these and 3 of these, we'll get sp3. If we take one of these and 2 of these, we'll get sp2. If we take one of these and 1 of these, we'll get sp. And that sounds very tricky, but I promise it's very straightforward. Don't foresee you will have any difficulty in determining hybridization. Couple key points here. The number of hybrid orbitals that you generate by hybridization is going to be equal to the total number of atomic orbitals combined. I'll show you that. When you form covalent bonds, you can get overlap of hybrid orbitals. And you'll see that molecular geometry is determined both by the shape and the orientation of these hybrid orbitals. And when I show them to you, I think you'll have a better feel for it. As I said, sp, you're going to blend 1s and 1p. sp2, you're going to blend 1s and 2p. sp3, you're going to blend 1s and 3p's. And let's take a look at these one at a time. I'm actually going to do it backward. That's how the slide progression is, but it doesn't really matter how you do it. Hybridization is when you mix atomic orbitals to form special orbitals, and these are for bonding purposes only. So for bonding purposes only, so not for lone pairs. With sp3, you're going to combine 1s and 3p's. If you ever need tetrahedral atomic orbitals, you're going to find that it will adopt a set of sp3 orbitals, and we say that the atom becomes sp3 hybridized. And that is what's shown here. In a free carbon atom, we know that we've got a 2s orbital. In the 2s subshell, we've got 1, 2, 3, 2p orbitals, 2px, 2py, 2pz. This makes up the second shell, and if we hybridize or blend them together, you get 4 equivalent sp3 orbitals. Same shape for each one, same energy for each one, and note the energy is somewhere in between the s and the p level. This is going to look really funky. You don't need to know what it looks like, but it may help you better understand. Here's an S, spherical. Remember, the P takes on a dumbbell shape oriented either about the X, the Y, or the Z axis. We're going to blend, and we're going to get 4 of the same sp3, and it makes this tetrahedral-like design that you will have a better feel for in the lab. And you can see it here a little bit better. This is methane, and I want to walk you through this very slowly so you can see how to determine it. If you were to draw methane, and again, I like to use the common names only because these are things you may see down the road, but the AP exam doesn't require that you know organic chemistry. Those of you going on to take Chem 2 subject test, there is a little bit of orgo there, and I'd be happy to show that to you separately. It's really very simple. If you were to draw methane, this one should be very simple for you to draw. This is back from honors or regular chem. Couple things I want you to see here. We want to look at the number of electron groups like we talked about last time. We want to look at electron group geometry. We want to look at molecular geometry. And finally, here comes the new piece, the hybridization. Remember we said a single bond, a double bond, or a triple bond is one electron group. So what we're looking at here is we have 1, 2, 3, 4 electron groups. And what's the electron group geometry? Tetrahedral. Remember, anytime you have no lone pairs on the central atom, the electron group geometry and the molecular geometry will be the same. So we've got tetrahedral molecular geometry. Hybridization. You have 4 electron groups. This is sp3. And the way you can prove that is if you add the superscripts here, 1 plus 3 makes 4. That's the key to doing it correctly. So if you add the superscripts there, 1 plus 3 equals 4, and you've got yourself a winner in regard to hybridization. It is the electron group geometry. It is the electron group geometry. It is the electron group geometry that determines the hybridization. So, we can consider 2 more molecular geometries that have this electron group geometry. We have ammonia, and we have water, and when we consider these 2, we want to know the number of electron groups. We want to know the electron group geometry. We want to know the molecular geometry. And we want to know the hybridization. Again, 1, 2, 3, 4, or 1, 2, 3, 4. They both have 4 electron groups. Therefore, they both illustrate tetrahedral electron group geometry. But they don't have tetrahedral molecular geometry. 3 atoms attached, 1 lone pair is trigonal, pyramidal. This one, 2 atoms attached, 2 lone pairs is bent. And again, those are molecular geometries from last year. We actually won't really be getting into the newer molecular geometries in regard to hybridization because they will not ask you anything past tetrahedral electron group geometry for hybridization. But both of these still illustrate sp3. 1 plus 3 is 4. They have 4 electron groups. So it is the electron group geometry that determines hybridization. And that's why even though the other day when we talked about molecular geometry, I did it from a perspective of electron group geometry, and I said to you they usually don't ask electron group geometry, they ask molecular group geometry, they ask for the shape. But you have to understand electron group geometry to understand hybridization.
How do you know it's 1 plus 3?
You're just adding the superscript. So after the S is an imaginary 1, so it's 1 plus 3, which must equal the electron group geometry. You'll see in the other hybridizations that it's going to be different. Give it a chance and it will click. I promise. All right, so there's methane here on the screen, but you see it for others as well because there are other structures that have the same electron group geometry. Next up is sp2. You're going to combine one S and 2 P's. You have trigonal planar electron group geometry. 1 p orbital is not used here. You don't need to know the orientation. Sigma and pi I'll hit in a few minutes. What you have here, S, and you're going to use 2 of the 2 P's to get 1, 2, 3 sp2 hybrid orbitals. You have 1, 2 p left over. And you would see this in ethylene. Don't really know if that's the easiest. It's not a hard structure to draw. Let's take a look. Ethylene actually, question?
Do the orbitals have to be filled?
No. Oh, I see what you're saying. Not always. Ideally, you want each element to have an octet of electrons. Hydrogen, of course, does not. With hybridization, let's hold that question and take a look right here because I think you're going to see it. I won't draw it yet. I'll draw it for you in a sec. So you've got 1 S and 2 of the P's. You're going to make sp2, 3 of them. This will start to get into it. It's going to flip to sigma and pi. I'll come back to sigma and pi, so I'm going to cut it.
The carbon-carbon double bond in ethylene consists of a sigma and a pi bond.
That'll come back.
An sp2 hybrid orbital on one CH2 unit of ethylene overlaps with an sp2 hybrid orbital on the other CH2.
So there are your 3 sp2 orbitals.
Unit to form the carbon-carbon sigma bond.
And I'll come back to sigma and pi in a sec. And I think the answer to your question is no. It's just not, it's not utilized in this particular instance because you only have 3 electron groups, so you only need 3 of the sp2s. So that other one's not utilized because there's nothing to put in it. So I think the answer would be no. But it's a good stumping little question.
So in that, then the SPX and XPY orbitals would both fill up with 2 electrons before the SPZ orbital gets 1.
If you had carbon, you would only utilize the X and the Y anyway. Correct. If you consider ethylene, which is C2H4, sometimes called ethylene, also called ethene, This is the gas that fruits give off when they ripen. This is why you don't leave bananas in paper bags, because they would be brown. Like sometimes you might have a nice yellow banana in the morning that you drop in your lunch bag, and by the time you open it up at 12:15 it's brown, and you're like, Well, that's because the banana gives off gas, and the gas is trapped in the bag, and as a result the banana just keeps feeding off the gas it's generating, and it ripens even faster. So here's ethylene, and if you were to draw it, I'm going to draw it as they did because it truly has trigonal planar electron group geometry as well as molecular geometry. And if you were to consider the number of electron groups, if you were to consider electron group geometry, molecular geometry, and hybridization, that's the new piece. Again, don't be confused. Single and double bonds count the same. 1, 2, 3. 3 electron groups. Trigonal planar. Anytime you have no lone pairs on the central atom, electron group and molecular geometry are the same. Now here's the hybridization. It's got to be equal to 3. So it's sp2, because 1 plus 2 is 3.
Dr. Hale?
Yep.
Why didn't you count the other two bonds?
Oh, both of them. These are the same. It's a symmetrical molecule. So this is sp3, and so would that. I was really just focusing on 1 carbon at a time, but they're the same in this instance.
No, I know, but why are there only 3 electron groups and not 5?
Because it's relative to the central atom. So when you're talking about electron groups, it's relative to each central atom. That's a good question, though. I didn't think of it that way. And for SP, it's a combination of 1S and 1P, so 2 of the 2 P's or the 3 P's or whatever P's are not used. This is going to give you a linear arrangement, and 2 of the P orbitals not used. You're going to need this for pi bonding. I'll show you that in a sec. Save a smidgy of room where you drew ethylene, because I'm going to draw a different one near it, but since I mentioned SP, let me continue with it and then I'll go back. What you're going to find here is a blending. Again, 1 2s, 1 2p, and you get 2 2s of equal energy, but you have 2 2p's that are not utilized. And you'll see this, for example, in carbon dioxide. Anytime you have a triple bond, you've got to have sp hybridization. So you're going to blend, and you've got 2 of them. You're going to have linear electron group geometry with a bond angle of 180. You're going to see this, for example, in carbon dioxide. We'll take a look. And again, I'm going to save a little room over here to draw a different structure. I'm going to come down here. I want to take a look at both carbon dioxide and hydrogen cyanide. We're going to look at and I hope when you come back from break you'll be professional drawers. The drawings are usually very simple. Don't think you'll have any difficulty with them. Most of you have very extensive drawing backgrounds, and you should be solid here. Number of electron groups, the electron group geometry, molecular geometry, and the hybridization. Both of these have how many electron groups?
2.
Correct. The electron group geometry for both of them is?
Linear?
How about the molecular geometry?
Linear.
Same. Now what about hybridization?
SP.
That would be SP because 1 plus 1 is 2. Anytime you have a triple bond, you're going to have linear, got to be SP. If you have 2 double bonds like that, as long as you're not expanding an octet, also SP.
So the hybridization is dependent on how many electron groups you have?
For sure.
Okay, I knew that.
All right. I just want to go back here for a sec because sometimes these come up and surprises are nice when you unwrap the package, but they're not fun on quizzes or tests. I want to go back. This is one of the resonant structures we talked about. I'm only going to draw one of them, but we know another resonance exists. How many electron groups does this have? 3 is correct. 1,
Because there's 1.
2, 3. And this still would be trigonal planar electron group geometry, but what's its molecular geometry? Bent is correct. But what's its hybridization?
SP2.
SP2 is correct because 1 plus 2 has to equal 3 electron groups. And that's every variation I can think of. You will see this in your lab, which I think will help. Years ago, you used to need to know the hybridization for 5 and 6 electron groups. You don't need to know that anymore for the AP exam. Basically, if you've got 5 electron groups, you add D to SP3. And if you have 6 electron groups, you add D2 to SP3. So you get SP3, D2. It's something that you might see in college chemistry, but they're not requiring it anymore for the AP exam. So I've crossed it out, and you don't need to do the hybridization piece for expanded octets on the lab that we'll move into in just a little bit. I've given you a chart here that I think would be helpful to you, although I think the drawings will do it for you. Let's take a look. We'll do the first one together and part of the second, and then I just want to show you sigma and pi bonding, and that'll be the crux of it today. For this first problem, it says describe a hybridization scheme for the central atoms and the molecular geometry of the silicon tetrachloride molecule. Then we want to know if it's polar or nonpolar, and we want to justify. So first up, we'll do this one together. We've got silicon tetrachloride, and this is going to look grossly similar to carbon tetrachloride, something you would have been able to draw at the honors level. We want to know the hybridization. We want to know the molecular geometry. We want to know if it's polar or nonpolar, and why. Okie dokie, hybridization would be? SP3 is correct. 1 plus 3 is 4. The geometry is? So here's the new piece. This is from last time. Now, I will tell you that silicon to chlorine, that's a polar bond. As is this, and that. is the molecule polar or nonpolar?
Non-polar.
Why?
Because it's
Because
a
they
natural
cancel.
symmetry.
All right, so we got to get the pieces down. It's a nonpolar covalent molecule. Because it is perfectly symmetrical. So the dipoles cancel. And again, you'd have dipole, 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 equal but opposite. That's like the four people picking up a body, one on the hand, one on the hand, one on the foot, one on the foot. You all pull in equal but opposite directions and you don't go anywhere.
I think we should try.
No, we're not going to try. Maybe with the stuffed animal. All right, the second question that is asked is about the triiodide ion. And this one you don't have to do the hybridization for anymore. This is getting to the level of AP. And we said whenever you're drawing an ion, absolutely, positively, pop it in the brackets with the charge so you don't do anything silly. Complete the octets of the terminal atoms, and then any remaining ones. Here's where electron count is going to be critical, because if you don't do it, you're going to forget some valence electrons, as we talked about last week. So we've got 12, 14, 16, 18, 20, 22. Now you're not responsible for that hybridization anymore, but what's its shape? Careful. 2 atoms attached, 3 lone pairs, and you're in the trigonal bipyramidal electron group family. This is the funky linear.
Oh, so they're not linear?
It is. In addition, this is neither polar nor nonpolar, correct? Because it is ionic. If it were an ionic, then you could see nonpolarity here. You've got equal but opposite dipoles that will cancel, and we talked about that in regard to the linear atoms. Those dipoles would cancel, and those lone pairs of electrons in equatorial planes that would cancel as well. But this is ionic. Careful. We'll talk more about the triiodide ion in the solution chapter.
Why is it linear, not dense?
These atoms are all in the same plane. These lone pairs make a triangle, and they have equal but opposite poles. And as a result, the molecule's not bent. Bent would be if you had 2 atoms attach 2 lone pairs, or 2 atoms attach 1 lone pair. But this is 5 electron groups, not 3 or 4. Questions here? The last piece of the puzzle is on hybrid orbitals and multiple covalent bonds. And I'll show you this in the images that I think will help. It says covalent bonds formed by the end-to-end overlap of orbitals, regardless of orbital type, are called sigma bonds. All single bonds are sigma bonds, single sigma. If the overlap of orbitals is in a parallel side-by-side fashion, you have a pi bond. A double bond has 1 sigma and 1 pi. A triple has 1 sigma and 2 pi bonds. Before we look at these examples here, I want to take a look. I'm going to go back to the original video because I stopped it. I'll probably backtrack it because it'll be easier for you.
Ethylene
looking
consists
at-
of a s-
We're looking at ethylene, and again, SP, SP2, or SP3? SP2, 3 electron groups.
sigma and a pi bond. An sp2 hybrid orbital on one CH2 and one CH.
So you have 1, 2, 3, 4, 5 sigmas and 1 pi. The sigma is an end-to-end overlap. Pi is a little different.
2 unit of ethylene overlaps with an sp2 hybrid orbital on the other CH2 unit to form the carbon-carbon sigma bond.
This is the end-to-end overlap, sigma.
Now we use a side-on view to show how the remaining unhybridized p orbitals on each CH2 unit overlap to form the carbon-carbon pi bond.
That's 1 pi bond. That's a little tricky, and you don't have to get so technical. Single sigma, double sigma, and a pi. Triple sigma and 2 pi's. It's not hard.
The carbon-carbon double bond in
We already looked at that 3 times. And here's carbon dioxide, where you've got 1, 2 sigma and 1, 2 pi's. Sigma's the direct end-to-end overlap. That and that makes 1 pi. That and that makes another pi. Let's draw a couple out here, and let's get the sigma pi. Actually, let's scoot down to the bottom for a sec, because sometimes on tests we do this. And let me lift the board here, because it's hard to put the lone pairs in from things you just pop off the internet. Let me just realign that. Come on down, baby. Oh, it moved. Let's see if I can move it this way. We'll just do it again. It's not okay. I tried to line it up. This is cocaine.
Do we have to draw that hexagon?
No. This is just something I popped off the internet, and I'll just show you how you can do it. On your test, I made it really clear with everything, but I want to show you that you can do it. This is very bad for you. You should not take drugs. I'm just completing octets here. These are condensed structural formulas that you don't typically see at this level. You'd see this more organic chemistry wise. When you look at these structures, wherever things meet, you have a carbon. You may or may not have a hydrogen that is shown or not shown. You typically don't show hydrogens like you do here, just so you don't have to spring it off again. But what I want to show you is right here. So here's N, and you've got 1, 2, 3, 4 electron groups. Couple questions in regard to that N right here. First of all, what would be its hybridization? It would be sp3 because you have 4 electron groups. What's its molecular geometry? What would the molecular geometry be? Not trigonal planar. Trigonal pyramidal. 3 atoms attached, 1 lone pair makes a pyramid. You'll see that in the lab when you draw it today. It will help. These two are going to be the same. And what would their hybridization be? sp3, 1, 2, 3, 4 electron groups. But what's their molecular geometry? Bent is correct. Okay? This one would be hard for you. I wouldn't ask it. This, I think, is fair game. Here you'd have a C, boom, 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 boom. So that hybridization-wise would be
SP3.
sp 3 electron groups. 2. 1 plus 2 is 3. But the molecular geometry here would be trigonal what? Planar is correct. Okay. I gave you an easier structure on your test with the dots already in. I just didn't want you to see this for the first time and be like, oh my God, what is this? Also, I wouldn't ask you sigma bonds on here. Who wants to count them all up, and it would be too tricky for you. But let's do pies. Everywhere you have a double, how many pies do you have? 1. 1, and you can slash them right on your test. It'll be easier. 1, 2, 3, 4, 5 pies. Okay? We're going to do another pi sigma, don't worry. No freaking out. Freaking out just makes us have a headache. Thanksgiving's right around the corner, guys. All right. In these two problems here, I'll draw them for you, even though you know how to draw. But you're going to be drawing like crazy in the lab as well as instructing. Okay. C3H4O, and you can draw many different isomers. Remember that isomers are not mirror images. You must move something, not just flip the molecule over. There are probably many possibilities here. Make sure each carbon has 4 bonds or it will cry. Do not expand the octet on a carbon because it's in period 2. These are definitely isomers. This is a ketone here. Is that actually a ketone? I don't think so. That's an alcohol. Regardless, I don't think they'll ask you to draw anything like that anyway. But let's take a look at one of the structures. We want to know hybridization and sigma and pi. So let's look here and here, and let's try and do this. You can just sit down in the back. Just give me a few minutes. So we've got 1, 2, 3, 4 electron groups. So what would the hybridization be? sp3. This one would be sp2. And this one would be sp. And let's do sigma pi. I think the easiest thing to do is get the pi's first and then just count the total number of bonds and subtract the pi's out. So how many pi's in this? 2. But all in all, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 2 is? 7 is correct.
How do you have 9?
I just counted sticks. 1, 2, 3, 4. I like to count in order though. 1, 2, 3, 4, 5, 6, 7, 8, 9. Like I'll count this line, then that line, then that line.
She counted all of them and then subtracted the pi bonds.
Yeah, I just counted all the bonds, which was 9, and 9 minus 2 is 7 sigmas. And the sigma pi on this will be the same, but the one I definitely want to make note of is this one for hybridization. What's the hybridization there? sp3 also. 4 electron groups, 1 and 3 is 4. And I will let you try cyanogen. Try and draw it and see if you can answer the questions. So cyanogen is C2N2, and see if you can draw it. Yes, but extremely unlikely. And if we try and build that in the lab, I don't think it'll hold. There's too much. Oh, wait, hang on, actually. I think there's too much torque on it. I don't see how you could get that bond in between, but you can try and assemble it. But I think you're going to have trouble doing it. When you try and assemble it, use the longest springs, but it's going to be tricky. Ready?
Yeah.
All right. Yes, yes? Is it a happy molecule? It's good? I can't emphasize enough the importance of practice. Please make sure you practice drawing. Make sure you practice molecular shape, hybridization, polarity. All of it will help you for your quiz next week after break.
That's Wednesday. We have.
I know, hang on a sec. Josh asked me one question about the lesson.
It's next week.
No, one question about the lesson. You understood every single thing?
Yeah.
I know, it's pretty easy.
Just like putting pylons, I was like, wait, didn't you mention this before? And then I was like, oh yeah, that's easy.
So you're good?
Yeah.
Anybody have any questions?
How'd you get the pi bonds for that?
Pi bonds, a triple bond has 2 pi's and 1 sigma. So 1, 2, 3, 4 pi's, 1, 2, 3 sigmas. All right, triple has 2 pi's, 1 sigma, double has 1 sigma, 1 pi. When you're triply full, you've had more pi's.
Thanksgiving.
All right, so that's everything in regard to bonding in terms of covalent bonding. We'll be getting into metallic bonding in a subsequent unit.